Hello, I'm John Samuelsen, and I'm going to be talking to you today about isotopes and their applications in archaeology. I am a research assistant at the Arkansas Archaeological Survey Coordinating Office in Fayetteville. I do a lot of research related to the Earth, I would say. You might call me an environmental archaeologist or geoarchaeologist. So a couple of things I do. I work on geophysics and isotope applications archaeology. So with geophysics, you would look at, you can use geophysics as kind of a technology to look beneath the surface of the ground to find evidence of past structures or settlements. And we can use that to better understand where people were and how they lived, and do that without having to excavate in many cases. So the geophysics allows us to see beneath the ground and without having to do the excavations. But geophysics is also a really important tool that can be used paired with excavations to get a better understanding of humans in the past. But today I'm going to be focusing on isotopes. So I've done some research with isotopes and focusing mainly in Arkansas. And in order to understand what isotopes can tell us about people in the past, it's important to really at least get an initial understanding of what an isotope is. So here I have a figure of a hydrogen atom. To be specific, 3 hydrogen atoms. So these are all 3 hydrogen atoms. One of these is way more likely to occur in nature than the other 2. And these 3 different hydrogen atoms are each called an isotope of hydrogen. So that's an isotope, that's an isotope, and that's an isotope. So those are 3 different isotopes. And what's different about them? Well, you can see here, one of them has 1 proton and no neutrons. This one has 1 proton and one proton and 1 neutron. And then this one has a proton and 2 neutrons. And so that's basically the difference. That's what makes them each a different isotope. But that also affects their weight or their mass. So in this case, this hydrogen isotope with 1 proton weighs 1 atomic mass unit. This hydrogen isotope has 2, so that's 2 atomic mass units. And then this one has 3, 2 neutrons and 1 proton. So that weighs 3 atomic mass units. And so what that does is each different type of hydrogen isotope has a different mass. And those are each different isotopes. So that's what isotopes are. It's essentially the same element in the periodic table that weighs different amounts because of the number of neutrons and protons that are in the isotope. The element is defined by the number of protons. So it's always, see how all 3 of these are hydrogen because it has 1 proton, okay? And then what makes it a different isotope is the number of neutrons that are there, okay? So that's what an isotope is. So these are things that occur in nature. So certain isotopes of hydrogen or any other element are common or are what we call abundant in nature. So each isotope has a different abundance. So that's the number, percentage of hydrogen atoms, for example, that are present in nature. So hydrogen has, one of those isotopes is about 99%. If you got hydrogen out of the air, it would be about 99% of them would be that isotope. And then the other 2 are much less likely to occur. And so that gives us a background for how to understand different processes and things that might occur that get deposited into your body and therefore tells us something about animals, plants, and humans in the past. So how do we actually use this stuff? So what we do is we can look at, for humans and plants, humans and animals, what we can do is look at this. This is a part of a deer jaw with teeth, with deer molars. And what we can do is we take a look at these deer and molars. We can take a portion of the enamel off of the deer molar. It's usually on a very small portion. And we take that enamel, and inside that enamel, it has remnants of the strontium that was in the teeth at the time the animal formed the teeth. So the different isotopes in the enamel or in dentin or in bone can be used to understand the environment that they lived in and what they ate or where they lived, based on the isotopes that are deposited in their teeth or bones. And so different isotopes, different elements have different relevance to us as to what kinds of questions they can help us address. So carbon isotopes help us address help us understand the types of plants and animals that were being consumed in the past. So for example, corn or maize tends to have a higher, what we call a higher carbon ratio, okay? So basically in that case, you're looking at different isotopes of carbon and how much of each of those isotopes are in, say, their bone. And that tells us, for example, if they might be eating a whole lot of corn or maize, particularly in the eastern US. And then if they have if they had a really high carbon ratio, that might suggest that they were eating a lot of maize. And if they have a really low isotope ratio, that might suggest they're eating other kinds of plants, not maize or corn. And then with nitrogen, what that tells us is about the trophic level of the humans and animals that were that we would test. So the nitrogen ratios would tend to be higher with higher trophic levels. So in that case, what that's saying is, like, the higher you are in the food chain, the higher your nitrogen isotope ratio will probably be. So herbivores are probably going to have low nitrogen isotopes. Omnivores are probably going to have isotopes in the middle, and carnivores are probably going to have isotopes at the top. But that is also different depending on whether you're talking about terrestrial environments or marine environments or freshwater environments. For example, fish, both marine and freshwater, tend to have higher nitrogen ratios than you might see from a comparable terrestrial animal. But that's all that information related to carbon and nitrogen is useful. They can be paired together, and they often are, to tell us about what people were eating in the past. Were they eating lots of maize and fish or corn, or were they eating other types of plants? Were they eating terrestrial animals? Were they eating lots of meat, or were they eating lots of plants? So we can basically look at all those different kinds of aspects of diet in the past. We can also look at other isotopes. So for example, there's oxygen isotopes are often looked at for where people are coming from based on climatic features. Strontium is commonly used for understanding where people are coming from based on geology. And I've been doing a lot of research recently with lead isotopes, which can be used in a similar way to strontium isotopes, although they're a bit more complex. And basically, what you can do with those isotopes, strontium and lead, is you can look at a geologic map like this, where you see different areas with different types of geology. Some of them are older, some of them are younger, some of them are just made up of different types of rocks and soil. And those different places with different rocks or soil might have different strontium ratios or different lead ratios. So for example, you might say here have really high strontium ratios, and then down here have really low strontium ratios. And so since people are eating plants in the areas where they are growing up as children, those strontium ratios they're eating from the plants and from the soil and the geology are working their way into their teeth as they are created in their mouths. And so the strontium ratios in the geology in the area where you grew up are being deposited in your bones and teeth. For archaeological purposes, for strontium and lead, the use of a tooth enamel is highly recommended because it's more resistant to contamination from being buried underground for hundreds of years can potentially affect the bone itself. So, but tooth enamel is much more resistant to that problem. So we typically use tooth enamel. Those isotopes can be used to answer questions about where people are coming from. So for example, did people migrate from up here to down there or something like that? So you can see people's movements in the past or where people are coming from. But we can also use those same isotopes to do some really interesting research on the ecology of certain areas, or where where certain animals or where people were hunting, or how they were hunting, like what kinds of animals were being brought in, what kind of animals were being hunted locally. And so as one example here, I've got a graph from some of my research, site in Southwest Arkansas, where we have, I've got strontium isotopes from soil at the site, and then we've got strontium isotopes of small animals here. So those are like squirrels and raccoon and things like that. And you can see there that the small animals look at least close-ish to the soil here. It's at least within the soil. And then you look at, by contrast, you look at these red ones here, and those are deer. Those are deer teeth, okay? So you can see that the deer are quite a bit different from the soil and the small animals. And what that's telling us is that the deer are coming from somewhere else. They're not coming from the site. So people might be hunting small animals like this from nearby, but those deer aren't coming from somewhere else. So what that can help us do is it tells us all kinds of things. So it can tell us about the diet, about where they were hunting, selective hunting in certain areas, or maybe where certain animals were more likely to live. Maybe, deer don't hang out at the archaeological site, which would make sense if there were human present. But the difference still suggests that the humans were going a fair distance. So now that can tell us about not only about the ecology, but also about the ceremonial uses of the site. So for example, this site was a multi-mound Caddo ceremonial site in Southwest Arkansas. And this site has significant evidence of ceremonial activity, and some of the deer came from those ceremonial deposits. And so what that's also telling us is that the deer are reflecting the humans bringing in deer from surrounding areas as part of the ceremonies where they would feast and have community activities. So it tells you not only about hunting behavior, but it also tells you about the community relationships between people and how they were bringing in people from surrounding areas, or bringing in food specifically for these ceremonial events. So anyway, all these issues, these are just some issues that you can deal with isotopes. Most commonly used ones, like I said, are carbon, nitrogen, strontium are probably pretty standard. But there are a lot of other types, but I hope this was informative, and thank you for listening.